In this lecture we're going to cover lighting, and really this is the other half of the BRDF function. So we've covered pretty in depth the material response that occurs when light impacts the surface and then reflects off of it toward the eye. So the main part of the question then for the light is what is its intensity, where is it coming in from, and did it make it? So the reason that's important is really for shadows, right? So we can, of course, keep track of where the light's coming from, where it's aiming, if it's spotlight or it's a controlled light rather than, say, a spherical light like the sun that sort of generally broadcasts in all directions. We might have a spotlight where we're assuming that the light only goes in a single direction, or the sun on the Earth is actually, by the time it gets to us, just directional rays, right? They're all essentially going in the same direction because the sun's much larger than the Earth. And so we don't see too much deviation in sort of the curvature of the light. So the interesting question with lighting, other than the color and intensity, which are just simple parameters that we might attach to our light values, is whether or not the light hits us, and that turns out to be fairly complicated, right? So you can see here we have a number of shadows on these stairs, and so for a given light source we have to go through and actually do kind of a collision detection sort of thing against all the rays to determine did the ray hit or not, and if it hit early then none of the rays are going to get through to this section. Or for this person here, as she's walking, we have to go through the full animation, and potentially we might imagine that we're actually impacting every single triangle that makes up the animated character that we might be hitting in order to determine whether or not we have a shadow. All right, so it's a potentially very complicated topic. However, there are two techniques that handle it for us, or potentially handle it for us, and one of them has kind of become the clear winner at this point. So the first technique is what's known as shadow volumes, and this was popularized by John Carmack in Doom 3, and then he did some invention in the process as well. And what happens is we treat the light as essentially a volume caster, and what we determine is the silhouette of one of the nearest objects, right, an occluder object like this one, and that silhouette from the perspective of the light, so the silhouette is along the edge here, casts a volume through the other objects. And so the way this is implemented is using the clip space in the graphics card, and I'm not going to go into detail on that. It's fairly complicated, but it's fairly complicated to understand. It turns out it's fairly straightforward to actually do. There are some issues with determining the inside and outside of the volume, and there's actually a technique known as the Carmack reverse that he came up with that very quickly solves the problem of if the viewer is inside the shadow volume. For the normal case, when the viewer is outside the shadow volume, so in all these cases here, we're not actually inside any shadow volumes. We're lit ourselves, and we're seeing objects that have shadows, but we're not part of it. And so there's some complications to that, but overall the algorithm is actually very fast and works very fast, of course. The main problem with the shadow volumes is that it is always hard edges, right? So we are casting the shadow this way. We capture a silhouette of this monster here by actually tracing the triangle silhouette. So we look at the outside edges. So a silhouette is always the outside edges of a triangle set that correspond to what the light sees, essentially the outside. And then the volume is cast down here. But the volume actually traces out that edge, and so it's a very hard edge every time. It's actually non-trivial, and I don't know that anyone has actually solved it to make soft shadows with volumes. So given that, there's another technique which is known as shadow mapping, which has really taken over and has become, as far as I'm aware, the most ubiquitous technique. So the idea with shadow mapping is that we reuse the same sort of frame buffer rasterization kind of approach, especially with the depth buffer, that we would render with the eye, and instead we do that from the perspective of the light. So we actually render the depth buffer for each light and figure out which surfaces are there. And then what we do is we use that depth buffer when we actually compute the shadow volumes and we do the same, we essentially, project our eye out, and when we capture the depth from any given point in space, we figure out where the depth of that point is relative to the light, so the distance to the light, and then we compare that against what the shadow mapped depth buffer is, right? So again, we figure out where this position is in space. We figure out its distance to the light, and that's also the depth from the light, right? And so we've already recorded where the closest objects are from the shadow map, right? So the depth buffer, if you remember, looks at all of the, so that all the nearest objects are darker in this case, and all the farthest objects are lighter or white. And so when we know the distance of a point in space from the light, then we can compare that point against here, and if the distance is longer, then it's brighter, a whiter value, and it might be behind something, we don't render the light for that particular point. Whereas if it's at least as close, and it could be exactly as close, because it could be actually the point that we used to actually render that point in the depth map, right? So that it could be the point that sort of corresponds to the nearest point that the light's able to see. And so that one does get light, right? And so that's kind of the notion of shadow maps. We're sort of reusing the whole frame buffer approach, but we're kind of using it from the perspective of the light. And so we have to render one shadow map per light, but we already know that we can render these things pretty quickly, and we're not doing a full render pass. We're not actually trying to color. We're not really caring about any of that. We really only need the depth buffer. And so we go that far, and then we stop immediately and save that out somewhere, and then we look it up. Okay. So it ends up being a fairly quick technique, and it's just at a base level, shadow maps are maybe a little slower than shadow volumes, simply because shadow volumes only need the silhouette for given objects that are impacting the light volume, and so they can control it. And the shadow map may see much more of the screen in some sense. But one of the issues that you run into with shadow maps is this issue of the resolution of the depth buffer. So if the light is far enough away, then the things it's seeing in the depth buffer go into a single pixel, but it might be that a single pixel, if you rendered it on, say, the car, right, so the light is far away, and this is essentially rendering the depth buffer at this point, right, or really it's rendering the depth buffer up here for this, this light pole. And so it's far enough away that all of this gets sort of captured as shadow points within the shadow map. And so this is kind of the trade-off. And so just given this instance, it actually sort of looks like shadow volumes are much better, right? Because we actually get clear and crisp shadows. It turns out that people have figured out good ways to work around that. So one of the shortest paths forward is what's known as cascade shadow maps. And what that does is actually captures, when you are capturing the depth buffer of the light, you keep track of where the eye is going to be, and you increase the volume, you increase the resolution near the eye, and decrease the volume further away. So near the eye, you get a high resolution image, and further away from the eye, the depth buffer for the light is much lower resolution. The strong point here is that shadow maps end up continuing to win the day, and there's continues to be resolution for them. The other thing that we can do with a shadow map is blur the depth buffer. So by blurring the depth buffer, we can then do soft shadows. So the reason these soft shadows are somewhat important is that what's really happening is if we had a point light source, right, that existed as a single point in space and was casting light out in a say perfect sphere, then we would expect that we would get the hard shadows, right? So these kinds of hard shadows that we're seeing here with this, well, that one too, but this hard edge right here is expected when we have a perfect point light source, or if we have perfectly horizontal lights which are directional from the sun. Now it turns out even from the sun we get a small amount of blending really close to the surface. So if we were to get down close, we'd actually see that even on Earth the sun does not appear as a point light source that is perfectly, either covering the sky as a full directional light source, or is it a perfect point light source, and we can treat it that way either. It's really there's some distance to it, so there's some amount of change over time. So uh, we can see this if we look at actually the what's known as the penumbra and the umbra um, of the sun. So if we look at this shape here, what we can see is that what's really happening is some of the light goes along the edge of the Earth here, right? And so some of this region is partially lit by some of the light coming off the sun, because the sun is larger than the Earth. So behind the Earth, this area is where the Earth is fully eclipsing the sun, and so we get a full sort of Earth eclipse, and all of this is in shadow. But at the edge over here, the Earth is not fully eclipsing the sun, and so there's some light coming through. It's a fraction of the amount of light, right? So that's where the penumbra looks like this, and we get a small amount of the light. It's not the full intensity of the sun, so we get less of it, but we get some amount. And so for a given light source, where it's probably much larger than the object that it's looking at, we should get some amount of soft shadowing. We should get small amounts of places where the light is partially coming through. It's not the entire light source, but it's most of the light source. And so that's what we want to get from soft shadows. And so by blurring the depth buffer, we can essentially simulate that for a given light. Right? The other thing that happens, of course, is that multiple lights impact, and then you get different shadows as well, and they soften that way as well. But for a given light source, because it doesn't perfectly capture the edges, we want soft shadows. So that's another place where shadow maps are successful. Simply by blurring the depth buffer, we can get that kind of effect. Now, I've mentioned that for each light we're going to have a shadow map, or for each light we might find the shadow volumes. And there's really two different ways now, two main techniques for finding each light, right? So the standard one, what's known as the forward lighting pipeline, has been the standard for a while, and continues to be good for certain things. And the idea here is that to capture multiple lights, we will clear the frame buffer, and then for each light, we will go through and we may actually have a first pass, which is our ambient light, or maybe even a global light if we're going to do that. But we'll capture that first, and then for each dynamic light in the scene, we'll go through and for each triangle, we'll render it, much as we did with the whole render pass, the render pipeline, which we've looked at in depth now, and capture all the materials and so on. But we'll do our entire material pipeline for that light, given that one light direction against every pixel within the triangle. And we'll capture of course, for every pixel in the triangle, we're also capturing the shadow map against the light source and determining whether or not that pixel is in shadow. But we'll do the full, the n.l in this case, and capture whatever our light value is for that pixel, given that light source, given the normal, everything that we already know, and we'll add that to the frame buffer. And then we'll go back again, and before we won't clear the frame buffer again, we'll go back to a new light, and then re-render the entire scene from the perspective of that light. So we actually render the scene every time for each light, and each time we render a light, we add it to the frame buffer. Now recall that when this is happening, it seems like we're going to add a whole lot of light, and we're just going to get sort of a white scene, because a fully bright scene, right? And what's really happening is that places that are not touched by any light are dark, or they're really just getting the ambient or global solution to the light, and so they're going to have minimum lighting of some sense, and the light's going to fall off. We have all these ways the light falls off, given distance and maybe and of course the direction, the fall off from the cosine of the angle to the surface, how perpendicular it is. We might even have a low intensity light, just simply in the first place. And so it's not necessarily true that we're going to capture, for any given pixel is going to be hit by that many lights. It might only be hit by one or two lights within the scene. You might have 2 or 3 lights actually impacting the camera at all at any given time. You might have many lights within your scene, but only a few of them in there. But the main problem here is really that if we do put in, say, 100 lights, then we really render our scene 100 times for each light. And if we're careful about it, we might see that some lights might be cold completely. We might say that, well, this light's never going to hit anything that I'm currently looking at, so we won't render that light. And that's fine. And we might say, some of these lights aren't anywhere close to the triangles I'm trying to render, and so let's ignore the lights for those, or maybe they're too far away or something like that. But even so, there's many cases, especially if you consider, say, a dungeon with torches lining the wall, there are many lights there, and so it becomes problematic in that case. Um, but again, it's kind of a known solution, and many of the techniques that we know for especially post-processing and doing other kinds of shader techniques and materials are all kind of written around the idea of having a forward lighting pass. But what if you do want to have many lights, right? So there is an alternate technique which is known as deferred lighting. And what happens with deferred lighting is that we actually capture many properties of the scene without sort of independent of the light, right? So here, what we've done is we've captured like the raw color, almost the raw albedo response of every object within this scene, right? And then we've also captured its depth. So we see, we're capturing the depth buffer here. And this again is all from the perspective of the camera for the final render. Right? So we have our color, we have our depth, we now have the normal, so we figure out the normal relative to the camera, right? And then we can figure out the shadow map relative to the light, right? So now what we're saying is we can compose these three images, and it's almost like what we talked about with the material pass in the first place, that we have normal maps and we have colors, and we're almost doing that from the perspective of the camera to render a single image given all of this information and of course a light direction or multiple light directions. And we do the final compose by saying we'll use these pieces of information against each individual light. So we render the light against these three pieces but not against the entire scene, and then we accumulate the light there. And so we know, of course, that for many lights, then they might not impact this scene, or they might be completely outside. So we can isolate the lights much easier that way. But it's actually not that costly to have, say, 20 or 30 lights maybe in the scene. And so if you have that long hallway where you do, have, say, a lot of torches along the wall, then deferred lighting is going to be the technique that's going to work better for you. But the alternative is that in some cases, especially in, say, the case where you just have a single light source like the sun, forward lighting is actually fairly straightforward and can render the single scene once, right? So you might capture your global illumination, and then you might capture the every triangle being rendered by the sun, and you write it out to your frame buffer once, rather than having to store multiple frame buffers of all of this information about the scene before you then compose it with a single light. So a deferred lighting setup doesn't necessarily make sense for one light. It might not even make that much sense for two lights, but by the time you get to 3 or 4 lights, it starts to become a little iffy, right? So is it better to render the scene with a couple different frame buffers and a couple different buffers, capture all these different versions, or is it better to render up to 4 lights this way and render the scene 4 times and accumulate it this way? So it's a trade-off, and one that you can explore because Unreal supports both. It defaults to deferred lighting because often you're inside in areas, and you don't lose too much by having deferred lighting for outside. But of course, you can then move from inside to outside very easily and have the right approach to the right thing, and even have outside lights impacting the inside light and so on. Now moving on, we did talk about reflections and sort of this environmental map reflection that happens. But really there's if we're thinking about the full BRDF function, then our light source isn't necessarily coming just from the light direction. It might actually be coming from reflected light from another source. And so this is really another part of the full solution. So we can of course think about direct lighting, and for many years that's really the only lighting we had. We have direct lighting with shadows and ambient light, and that worked very well for Doom and Half-Life and many games like that. But we're finding that we can compute global illumination in baked time, near real time, and we're starting to get to the place where this becomes something practical for full lighting and has a lot of impact on that lighting, on the scene itself. So what we have to consider is that our light sources don't always get fully absorbed, right? So ray tracing was a technique where it's kind of the Phong model of global illumination, right? So we sort of assume that our surfaces are very reflective, that they're kind of that specular reflection kind of case. And what we do is for ray tracing, we cast a line out from every pixel toward the scene itself, and that line will, bounce off of various triangles, and we'll follow that bounce, and we'll actually follow the ray off to the next surface. So we might hit this green surface here, and we might hit the blue surface, then we might come back and hit the green surface again, then we might hit the blue surface, and that's why you see multiple copies of the image right there. And just to step through it a little more carefully, you can see that we again use our spectator in our near plane, and we cast rays from the point of the spectator in the direction of the pixel, and then follow a surface, which in this case is a mirror, and we find the reflection, and then we trace that line and then reflect off of the scene object and find our light ray, right? It says shadow ray there, but I think that's actually a light ray, and so it's therefore a lit piece. Whereas here we see different different source, right? So this is the full technique, and again, there's some of the cases for probability. One is, of course, where you're actually passing in the pixel. You might actually pass multiple arrays through an individual pixel to sample the scene with like small variations within the pixel. But you might also have different kinds of reflection rather than simply the perfect reflection at every point. And so you might actually resample the reflection of an object through a few different sort of recall the sort of microstructure of the surface. If we consider a sort of non-uniform surface, we might actually want to cast the ray in a few different directions to sort of simulate that. And so as you can imagine, you have to cast a lot of rays to make that work. And you actually have to cast a lot of rays with minor variations with a random distribution, which is known as a Monte Carlo kind of distribution. And so a lot of the ray tracing techniques actually use a Monte Carlo cast to solve the problem. And now that we're using that in many cases for real-time lighting. So we use a Monte Carlo kind of technique where we randomly sample the space and then sort of fill in the blanks in some sense. So this idea is actually turns out fairly straightforward to implement if you feel comfortable with the idea of recursion and just capturing that first reflection. You simply just recurse for a little while and decide whether or not you hit a light source or not. It's surprising to think that it works because it feels like you might never hit the light source. And there are, of course, techniques that do cast rays from the light source and from the eye, and then they try to figure out where they meet using some kind of sort of volume of collision and so on. But this technique really captures full sort of reflective lighting in the environment, right? So all of the rays are cast out. We're almost casting our photons as individual lights, but not in the billions, but maybe in the millions to cast this. And up till very recently, ray tracing has never been considered a real-time technique. It's something that you do to get a very nice reflective scene like this one here, but it also might take 4 to 8 hours to actually compute a single image. So we talked about the Phong model of global illumination. Radiosity, in some sense, is like the Lambertian models. This is really assuming sort of that rougher surface, right? So I mentioned that you can kind of simulate that with ray tracing, but ray tracing is really kind of meant for capturing the hard surfaces that are highly reflective, and you can just use the single reflection vector to capture that if you want to properly. Otherwise, you have to sort of cast many more rays, and it becomes a combinatoric nightmare. But radiosity is built in a different kind of way. It's actually assuming that every surface is fairly rough and that they're all going to cast light out in a somewhat uniform direction based on the intensity of the light that comes in, right? So if you recall, we really, understand that the intensity sort of falls off with the cosine of the angle between them, and we get the cosine law of lighting. And so as we're sort of, more perpendicular to the direction of the light, we get less of the intensity of that light coming to us. And so we take that to an extreme and find every little piece of surface here that gets any kind of light from any source, right? So we've got the red light actually impacting the surface here, and the blue light impacts it over here, although you can't necessarily tell because you do see some blue lighting on the floor here from the reflection between these two. And the same with the red coloration right here. So, so what we do with radiosity is essentially break the whole scene into a whole lot of patches. And we do that by determining where the light is hitting. So we actually calculate that a whole lot of these regions are hitting kind of a uniform source, and they're really just it's kind of a shadowed area, and so there's not much reason to break it up much further. Just say, well, here's a large patch. It's getting a somewhat uniform amount of light into it, and then here's some other patches where it's actually very non-uniform. We have to find some detail. But overall, we can break these up into patches, and then these patches are essentially what we're reflecting back out, right? So this becomes both the surface, in some sense, the light surface that we've recorded and captured based on our BRDF for that original surface, but also essentially every one of these patches then becomes a light source to the scene, right? And so what you can imagine is there's kind of this recursive structure where this piece becomes part of that piece and so on. And there's actually the techniques here involve kind of a relaxation with a very giant matrix. It's a large adjacency matrix where they say how close am I to every other single patch within this scene, and we relax the whole thing through through an optimization technique, and we find the sort of optimal way of capturing the whole light of the system, right? All the lights coming through. You'll notice too that even the light source in this case suddenly becomes a patch, right? So it's a patch that is at full intensity. Everybody else kind of gets the intensity plus their color, but the light really starts as a patch itself. Again, looks like that. So when we capture the light map, so I mentioned that we're breaking this down, we're finding out what the lit surface looks like. What this actually gives us is pretty much an intensity and color map that then we can save, and it's a map that is essentially a texture map, right? So we're capturing a slightly different sort of UV structure. So we capture whatever UV structure we need over here. So usually you have what are known as light UV coordinates, which are added to or modified on your object and then used as part of the light map structure. And so all these objects get baked into a light map texture, which then they can go sample from to figure out the light portion, the global illumination. So when you bake out a scene like this, what you're baking out is a texture map, which is very, very similar to the ambient occlusion map, except that in the case of the ambient occlusion map, what we're capturing really, or the important piece of that is it's uniform white unless we're in a shadowed region, because again the white color in color space just gives you back the same color. So when you multiply it, you just get your same color back. So you have a full intensity source, whereas with the darker colors, then you get a degraded intensity. You get less intensity from the light, so you get the shadowed regions. So that's the purpose of an ambient occlusion map. The light mapping in this case is kind of the opposite. We're actually assuming in most cases that we're in shadow, we're not lit at all, and then the light map tells us where we're going to get new lighting, where we're going to get additional lighting. So it's not necessarily strictly multiplicative, it's actually additive for each light that's available, or just overall against the scene, and especially against dynamic lights in the scene that may not have been part of the bake or other aspects like that. So rather than simply being a hard shadowing that happens, it is now a lighting itself. So up to this point, we've been treating the frame buffer as a series of 0 to 255 values, so a single byte for each of the RGB, which lets us cover an intensity range for each of those of exactly 256 values, going from 0 to 255. Now this is sufficient to capture a lot of the details in terms of what kinds of colors we can see. So the hue represents sort of the color, and then we think of the term saturation as whether it's bright red or a faded out red, right? So a low saturation means it starts to look more like a whitish red or a grayish red. And so we can capture a lot of the range of hue and saturation that our eyes are able to see, but we're not able to capture a lot of the intensity. Our intensity values are very limited, so we really only have exactly 256 levels of intensity. So real light goes from 0 to essentially infinity, right? Now we never really have infinity photons, and if we did, it's sort of a laser beam, right? That at that point it might actually start cutting into things and certainly burning out your iris. But a 0 means that there's no photons, and there's sort of no upper bound to the number of photons we can see, right? So the sun is blasting us with photons constantly, right? Billions and billions of photons per second. A standard lamp that might be sitting on your desk or your monitor right now might be more like the millions, right, of photons, but it's still many, and so we're still seeing that as well. So there's a huge range in which we can see things, and your eye is actually able to detect even a single photon. So if you're in a completely dark room, and a single photon is bouncing around and hits your eyeball, you will detect a brief flash, right? It's very brief, it's very small, but your eye is able to respond to even that level of detail. So our eyes are able to capture this, and cameras, to some degree, are able to capture a much wider range than we might be able to do with the monitor. So what do we do? Well, there's a couple ways to modify things. So all monitors are going to pick some level of intensity, right? In terms of the actual brightness that is represented by, say, a 255 on red, they're going to pick what that intensity is in terms of essentially the amount of photons that are coming off of that pixel into your eyeball. And that intensity is going to be much less than the sun. But you might have some monitors that have a smaller response curve in some ways than other monitors. Some monitors are much brighter than others, or TVs or projectors are each going to have different values there. And so the levels of intensity there might not be the one you want, right? And this is where gamma correction comes in. So there is a curve that the monitor has, and it's not necessarily linear either, right? So it's not that 0 to 255 goes a straight line. There might actually be some curvature to it. So there are a few ways to adjust, your levels that you're working with in terms of brightness and contrast outside the monitor. So obviously you can go to your monitor's brightness and contrast settings and adjust those, and you'll see that games will offer you a gamma correction to deal to sort of set the gamma in the first place. That whole thing where you're seeing a barely visible icon on the screen, and you want to set it to where it's just barely visible. But then within the game, they're gonna do often, especially now, tone mapping or exposure, which actually model a physical process. So tone mapping was a process of essentially setting the curve, especially when you're trying to expose film and actually get the process of developing film and the chemicals you use to develop it. You can shift the curves for each of the red, green, and blue, and so they would use different processes to shift those curves to try to get to shift the intensity where it was useful for the image, right? And so in some cases you could play around with the color that way. Exposure is really about dynamically correcting for the scene, right? So if you're in a darker scene, you can actually up the exposure. You can think of it as your iris closing or opening. When you move into a dark room, your iris will open up wider to allow more, to increase the exposure and allow more of the lower level intensity in. Or if you go outside, your iris will contract and lower the total intensity, increase or decrease the amount of photons that can get to your eye. So let's take a look at what that looks like in practice. So I've got an image here, and I'm in the GIMP and I'm playing around with the curves right here, and I'm just going to play around with the level curves. So if I wanted to decrease the contrast in this scene, I would leave the center line here in the middle, so I'm going to keep the brightness about the same, and by lowering oops, I'm going to keep it in the middle there so the brightness is the same. By lowering the range, essentially, that this curve can follow, or this line is following, I get a lower contrast image. Now if I shift the whole line up or down, so I shift it down, say, this way, now I get a dark and low contrast image, or a darker and low contrast image. Or if I shift it up this way, then I get a brighter and low contrast image. On the contrary, I can also say I want to increase the contrast by creating a steeper line here, And again, I've got some a fixed level of brightness. I could reduce the total brightness like that way, and so I can play with this as a line. And the way to think about it is that contrast is the slope of the line here, and then brightness is shifting the line up and down. Right now, gamma is actually applying a curve. So the monitor's response is nonlinear and will apply maybe more brightness over here, or maybe less brightness over there, right? So some monitors might be washed out and actually have a brighter or a higher sort of low range over, or more range over here and less range up in the white area, or they might have a better white representation region and lower contrast down here, say. So essentially, this is kind of playing with the gamma curve of the response of these RGB values, and then it can adapt to what the monitor's doing. And then tone mapping and exposure let us just play with these dynamically, right? So usually it's going to be at the form of modifying this curve to some degree, depending on the nature of the scene. So if it's a darker scene, we might bring it up, and if it's a lower, brighter scene, we might bring it down. And we can play around with those values dynamically within the context. And Unreal, as we've already seen, Unreal has the ability to allow us to change the exposure. So we're seeing that in the material setting, and of course in the game itself, you're able to play with those values. So one of the other assumptions that our lighting makes, and this again comes back to how we solve the BRDF in general, is that our lighting is actually flowing through clear air. So that's the assumption, and that's never the case actually. So regardless of where we are in space on the Earth, usually, actually if we are in space, then we are floating through clear air essentially, because we're in a vacuum. But if we're on Earth, then there's actually oxygen molecules in the air, there's nitrogen, there's small water, some dust particles, and all of those things impact light coming from the sky. So the reason that the sky is blue is that that's the color that reflects the most. And so the sun is hitting the atmosphere, and most of the reflection, it's on the slower, like blue is on the slower end of the spectrum. So it gets reflected more, it gets deflected more, because it's lower, or moving slower in some sense. And so so those are the ones that get deflected, and that's the color that we end up seeing. So that's actually why the sky is blue. And then that's also why the sky is orange at sunset, because that's the color that comes through. So all of the blue light gets deflected, and what's left is an orangey reddish color that's tending to come straight through, barreling straight through, without getting scattered as much. And so that's kind of the sort of default setting just for our world. But of course there's a variety of ways in which light can be scattered and sort of has a volume shape to it, in that it moves through space and has to get impacted by that space. And there's a technique known as ray marching that kind of captures that specifically. It actually can capture both the foggy bits and the part that's solid, that's through it. But the idea is that as you're marching through space, right? So if you just capture from your eye, and we imagine that there's some level of density of the fog, the further you move into the fog, the higher the probability that you're going to be scattered. And there's both an in-scattering and an out-scattering. So out-scattering is the idea that light that would have come and hit you has been scattered away, and so that density decreases. And in-scattering is the notion that light that's bouncing around inside the fog will happen to come your direction, and so there's the intensity increases from the in-scattering. But usually there are two different values, right? So the out-scattering, say in the case of the sunset, the orange hazy sunset, the outscattering actually tends to hit primarily the blue colors, and again the blue color will be the one that in-scatters, but it'll be less likely to in-scatter in your direction. So you might get some off colors coming from other things that are scattering to you, or just a general capture of sort of the dust particles or whatever's scattering there. But the outscattering removes all of the blue in that sense. So that's kind of the a general technique that's used, but there are of course many variations to capture that, and we're not going to worry too much about that. You'll be able to look at the techniques that you have available through Unreal. But again, the thing to understand there is that you can modify the density of the air, or the medium that the light is passing through, and by doing so, that causes the light to shift and be modified in some sense by that. And usually it's because it's being bounced off away from your eye, or being bounced in towards your eye from some other source, whether it's maybe bluish or reddish, depending on that. So a couple sort of boss level techniques. Clouds are actually incredibly difficult to model, in part because they are a challenging fluid dynamics simulation in the first place, just to get the right sort of density of water vapor to air, and the mixing that happens, and where those densities increase or decrease, and where the edges are. And you actually create octrees down to say small levels of detail, or in other words voxels, that capture quality of the fog. But if you want to down, it's kind of both a macroscopic and a microscopic effect, and so it's very hard to get fog right, because it's sort of got a lot of fractal properties to it, that it both exists with a macrostructure and a microscopic structure as well. And so it's very hard to do, but there are certain techniques that sort of solve that. We won't go into it, but I just wanted to mention that this is kind of why you don't often see realistic clouds in weather, where especially weather that you can fly through, say in simulator, or that especially is dynamic and constantly changing. Now I may be proven wrong by, say, the new Microsoft Flight Simulator. They may have actually found out some cool techniques to solve that, and they may have focused specifically on getting the fluid dynamics right for that. But it is a very difficult problem to solve, and that's why you often see just sort of pre-recorded clouds, or just pictures of clouds on the skybox. The other one that's kind of challenging, and this has to do more with the scattering. So water is much like the air in some sense, except that it's more dense, and there's a lot of really complicated effects that happen, not just at the surface, but also through the water itself. And so that's partially why it's got this bluish color, because the light actually does get fully scattered, and so there's actually maybe a lot of in-scattering that happens from water that causes light to shift that way. And many games can get away with a lot of good techniques to sort of make that work, but capturing the full range of things that happen underwater is actually fairly challenging, because there are so many techniques. And it's similar in a way to clouds, because again we have a surface that is fluid dynamic, and the bends of the surface actually cause lensing effects on the light itself, so you actually get dispersions and focal points, what are known as caustics as well. So caustics are where light actually ends up focusing, like with a magnifying glass, and creates a higher intensity beam, because whatever the light source was initially, it actually ends up being higher, because multiple deflections are causing the light to impinge on a single point. So you actually get more light coming into that single point than you actually had sort of originally if say this object wasn't there at all, right? So these kinds of caustics, and then of course you can see similar kinds of bending occur from the change. So because the light's bent so severely, you start to get the fracturing of the red to blue shift. So you actually see the scattering sort of in real time from these kinds of hard scattering surfaces. This one's actually so this kind of technique is known as photon mapping, or the technique that captured this image here, and that one's not really real time at all. It's a sort of a very advanced kind of, it's almost like a scattering plus ray tracing technique that captures both the light onto a surface, moving through the surface, and then leaving that surface as well. But you're able to capture some of these really great like weird things that light does, especially with fully transparent sorts of objects like glass or water that you get. And many games, of course, fake these kinds of techniques, because as long as you put enough noise into it, especially with water and it's moving around all the time, you get kind of the same thing.